Again, hello everyone. In my previous video, the last portion was cut off because someone called me. Okay, so this was my picture. Okay, this is continuation from the previous video lecture. So here I have an object. My applied force is 50 Newton to the right. There is a friction force 10 Newton to the left. And the other forces here are, you can have gravity here, F of G, which is mass times gravity, and there is a normal force. So the question here is, calculate the work done by each force. Number one, calculate the work done by each force. Okay, and the second question is, calculate the total work done. Calculate the total work done. Okay, this is really simple problem. So to calculate the net work done, so you can calculate, like you can start from here, work done by gravity. This is F of G gravity times D. Okay. So here, this is, you can do this F of G D cosine theta. Theta is, look, displacement is this direction, force is this direction, theta is 90 degree. So this is simply 90 degree and this is equal to 0. So work done by gravitational force is 0 here. Similarly, work done by normal force, you can also write down Fn d cosine. Again, here is the normal force, this is the normal force, and this angle is 90 degree. Again here this is 90 degree, so simply this is also 0. Work done by normal force is also 0. And work done by applied force, let me write down F of A. This is F A D. Now look, this is your applied force and this is the displacement, so they are parallel. That means the angle between them is 0 degree. So you have to write down cosine 0 degree. This is simply F A times D. F A is 50 Newton. Your D is 20 meter. So this is, I think, please use your calculator. I think this is 1000 joule. Work done by applied force, that is 1000 joule. Now what about the work done by friction force then? So work done by friction force, this is equal to force of friction D. Now okay, look here, displacement is this direction, this is the direction of displacement right here, and this is the direction of force. So this angle, this is 180 degree. Okay, so you have to write down 180 degree, but cosine 180 degree, not only 180 degree, cosine 180 degree. Cosine 180 degree is -1. So you can simply write down negative force of friction D. Okay, plug negative force of friction. The force of friction is 10 Newton and displacement is 20 meters. So this is negative 200 joule. Okay, so again, the work done by friction here, I get negative force of friction times D, because my cosine 180 degree, that is -1. Or simply keep in mind, the work done by friction is always negative. You can directly write down this number, negative force of friction times D. You can use this formula. So now I calculated the work done by gravitational force, which is 0, work done by normal force, this is also 0, work done by applied force, and work done by the friction force. That is the answer to the first questions. Now what about the second question? What is your total work done? Okay, it is really simple. The total work done, W total, you know, I told you work done is a vector quantity, scalar quantity. It is scalar quantity. So simply you add them. Work done by gravity plus work done by normal force plus work done by applied force plus work done by friction force. Because work done is a scalar quantity, so simply add them. This is 0. This is also 0. Work done by applied force is 1000 joule, and work done by friction is negative 200 joule. So this is 800 joule. That's it. So this is the net work done. Or if the question is what is net work done only, if you do not have to calculate the work done by each individual force, first you can calculate the net force. So here you have a applied force 50 Newton. Okay, you have a friction force 10 Newton, and your displacement here is 20 meters. Okay, 20 meters. Okay, so to calculate the net force, just simply calculate, to calculate the net work done, total work done, calculate the net force first. Okay, so what is your F net? Your F net, this is equal to, look here, Fa is to the right positive 50 Newton, minus friction force is to the left 10 Newton, that's why it is negative, so you write down 10 Newton negative, and this is 14 Newton. So the net force acting on this object is 40 Newton, and you have a displacement 20 meter. Okay, so your work done W, this is simply F net times D, and this is F net is 40 Newton, and displacement is 20 meter. Therefore, this is 800 Newton meter, or you can write down 800 joule. This is also the same thing. This is the total work done. But if you have to calculate work done by each force, then you use the previous method. Okay, so whatever method you use, that's fine, but you have to use very in the correct way. Okay, so this is how you calculate the work done. So always keep in mind the force and displacement, they must be in the same direction. And if the object is moving, but if there is no force in the direction of motion, no work is done there, and work done is a scalar quantity, and here this force, or whatever force I use so far, the force is constant force. So this formula, this is for the constant force. Okay, what about the work done by changing force, variable force? Work done by variable force. Work done by variable or changing. Work done by changing force, variable force. So in this case, how do you calculate the work done? Simply, we do not apply the formula here, because we can apply the formula, but I need a integral calculus for that. We cannot use a calculus here. Simply, those who know the calculus, your work done, simply you do this work done is integral, the sign of integration, fx dx. This is how you calculate the work done using the calculus, but you are not allowed to do this. Okay, here the force is function of x dx. Okay, so but I'm not allowed to do that. So if you are not allowed to use the calculus, then you have to do the graphical method. Okay, so let us suppose this is your displacement here. Okay, and here you have a force. Okay, and if your graph is something like this, whatever, like this. So how do you calculate the work done? In this case, your work done is very simple. The area under the graph, this is the graph, this is a curve, this is a curve. It is not necessary, whatever, this is your graph. If it is curve, a little bit difficult. Okay, if it is curve, it is a little bit difficult. If it is a straight line, then you can use a formula like a, the area of the triangle, rectangle, something like that. So in this case, the work done is given by the area under this curve. Whatever area you have here under this curve, that area gives you the work done. The area under the curve, area under the graph. Or if you have a curve or a straight line, it's not a big deal. Area under the graph gives the work done. Okay, so how do we get the area then? So because if this is a straight line, I think you can easily get the area, but if it is a curve, then you have to divide this like this. You make a grid, okay, you make a grid, and right there, draw the line this way. Okay, now look here, this is rectangle, you can get the area of this rectangle. This is also rectangle, you can get this area, the highlighted area only. These all are rectangle here. Okay, so you have 1, 2, 3, 4, 5 rectangles, and you know how to get the area of the rectangle. You multiply simply this length and this length. Okay, so if you multiply this length and this length and width, you multiply the length and width, you get the area of the rectangle. So get the area of all 1, 2, 3, 4, 5 rectangles here. You can draw more than 5 if you want the really better approximation. So get the area of these all 5 rectangles here and add them together. You get the total work done. But look here, you get this area, you get this area, here also you get this area, but you ignore this portion here, you ignore this portion, you ignore this portion here, you ignore this portion, you ignore this portion, you ignore this portion. That's why we call this is approximation. You do not get exactly the accurate work done here, but you get the work done very close to the accurate number. So if you want to include this area, then try to make more rectangle than if you draw this like this. Okay, and draw the triangle, the straight line here. Now look, you include this portion, you include this portion. So anyway, if you make many rectangles, that means your approximation is better approximation, but still that is approximation. We cannot include this kind of area. If you draw many rectangles, you include more, but not 100%. So this is the approximation. So again, if you have a changing force, variable force, you have to draw the graph, and simply the area under the graph, that gives you the work done. Okay, that's it. And in the exam, or we can give you some types of straight graph like this. Look at this. Okay, this is your F and this is your F, and if your graph is something like this, so here you have some number here, whatever you have, to 20, 40, whatever, and maybe here you have a 10, and here you have like a negative 10, and this number is 5, 10, and like a 15, something like this, you know. Now, how much work is done here? What you have to do, what I told you, the area under the curve, the area under the graph. So first look at this, this is the curve here. First get this area. What is this? This is triangle above the x-axis. Get the area of the triangle. How do you get the area of the triangle? Area of the triangle is 1/2 times base times height. So you can easily get this. All these, they are straight line. Get the area of this triangle and look at this. This one, this is also the triangle, but it is small. Okay. So get the area of this triangle. So here let me call the area of this triangle is A1. Area of this triangle is A2. How do you get the total work done here then? Your total work done, W total, this is equal to A1, it is above the x-axis, so simply you can write down positive, and whatever number you get here, it is down below the x-axis, so negative A2 then. So if you get 10 from here or whatever I put, if you get 10 from here and 5 from there, so 10 minus 5 is 5 joule. That is how you have to calculate the work done. Okay, if you don't have this portion, then in that case, just simply the area is this triangle only, and work done is only the area of this triangle if there is no the little triangle there. So again, the work done by changing force, you need to use the graph. That's what you need to know. Okay. Okay, so that is all about the work done. I think this is pretty simple, but you have to do many problems. I will assign the worksheet and homework also. And another topic is energy. So let us discuss a little bit about the energy first, the definition. What is energy? Simply, you need force, to do something, and to generate some force, you have to eat something. That means, and if you don't eat food in a few days, like if you don't eat food today, tomorrow, then definitely day after tomorrow you're gonna do anything else. You do not have any capacity to do the work. So simply energy, it is capacity or ability to do the work. This one energy, this is ability to do the work. There are many types of energy, different types of energy. One simple is you can call mechanical energy. Mechanical energy. Okay. Under this mechanical energy, we'll talk about like kinetic energy. We'll talk about the kinetic energy. We'll talk about the gravitational potential energy. Gravitational potential energy. We'll talk about the elastic potential energy. I'm talking in this class, I'll talk about the kinetic energy, gravitational potential energy, and elastic potential energy. But you have like a electrostatic potential energy also. You have to do that in physics 121. So I don't worry about that. So we'll do mechanical energy. You have like heat energy. Heat energy. We'll also talk about the heat energy in this class in thermodynamics. We'll also talk about the chemical energy. In fact, the chemical energy we do not focus that here. Basically, I'll focus on the mechanical energy and the heat energy. But I'm talking there are different form of energy. Heat energy, you can say like light energy. You have like electric energy, nuclear energy. There are many forms of energy: heat energy, light energy, electric energy, nuclear energy. Like solar, that is also the form of energy. That is a light energy. Even sound, you can call sound energy. The magnet, that also has the energy. So there are different form of energy. But in this class, simply we'll focus the mechanical energy first. And so in this chapter, we talk about the mechanical energy, and in future we'll talk about the heat also. In chapter 13, heat and temperature, we'll talk about the heat energy there. So the energy, it is the ability to do the work, and we have a different types of energy, different form of energy. You can see in our environment also, we can see the light energy, we have a heat energy, we have a sound energy, we have a chemical energy, we have a nuclear energy, we have electric energy, many different form of energy. Okay. So now, under this mechanical energy, we have a kinetic energy and potential energy. Kinetic energy, there are two types of kinetic energy: translational kinetic energy and rotational kinetic energy. Okay. So we have to discuss both, but here I simply do the kinetic energy, translational. So let me write down kinetic energy. We simply write down Ke. Okay, so this is the translational kinetic energy. I do not introduce the rotational kinetic energy here. So whatever we talk here in this chapter is translational kinetic energy. Let us suppose this is the object. Object has a mass m, and this object is moving with a speed v. So this object possesses some energy if it is in motion. So simply the kinetic energy, we say that energy associated with motion. This is your kinetic energy. If the object is in motion, this object has some energy. That energy is called as the kinetic energy. And the formula to calculate the kinetic energy Ke, this is equal to 1/2 mass times speed square, 1/2 mv square. So this is the formula to calculate the kinetic energy, 1/2 mv square, kinetic energy. But again, any form of energy, they are scalar quantity. Okay, please don't confuse. Energy is a scalar quantity. Energy is a scalar quantity. And the unit of energy is, the unit of energy, it is joule. The unit of energy is joule. Okay, the unit of energy is joule. And here whatever you have kinetic energy, potential energy, like electric, whatever, we simply use the SI unit is joule. Okay, joule. So to measure the kinetic energy, you have to write down this 1/2 mv square, or the formula to calculate the kinetic energy is 1/2 mv square. Okay, so like a bullet is moving like at 400 meters per second, really high speed. In that case, the bullet has a really huge speed. Mass is small, but still the bullet speed is really big. That's why the bullet energy is really high. That's why that is dangerous. If bullet strike here, I die. Okay, so the bullet has a really high energy. Truck, several kg, very big. The truck, if it is moving like a 0.5 meter per second, moving slowly, but still the truck has a big energy. Why? Because its mass is really big. What am I saying here is kinetic energy. It depends on mass, it depends on speed both. Okay, so please keep this in mind. Okay, let us discuss more about the kinetic energy. We call work energy theorem. Work energy theorem. Okay, let me give you the example. I want to start from here. This is the horizontal plane. Okay, horizontal plane. I have an object here. This object has a mass m, and this is 5 kg. And right here, this is the initial position, and here the initial speed of this object v0. Let us suppose this is 5 meters per second. After certain time, this object reaches this position. Mass is again same object, but here your final velocity is let's say 10 meters per second. 10 meters per second. Now my concern here is I have the mass of an object which is 5 kg, and I have my initial velocity 5 meters per second, final velocity 10 meters per second. But the concern here, or the question here is how much work is done to go from A to B. A to B. I don't know the displacement. I don't know the force. I don't have force there. I don't have a displacement there. I don't know that. It is not given. But still the question is how much work is done to go from A to B. How do you calculate the work done? Okay, in this case, here I do not know the force. I do not know the displacement. But how do you calculate the work done? So in this case, simply the work done is W. This is equal to change in kinetic energy. The change in kinetic energy, that gives you the work done. And this is called as the work energy theorem. Again guys, the change in kinetic energy, that gives you the work done. So you can write down W equal to delta KE, or if you want to elaborate this, delta KE, you can write down KE final minus KE initial. Okay, so KE initial. So what is your KE final? KE final is 1/2 mv square. This is your final kinetic energy, minus KE initial is 1/2 mv0 square. Okay, now you can calculate the work done. So if you want to write down the formula, W work done is 1/2 mv square. This is your final kinetic energy. 1/2 mv0 square. This is your initial kinetic energy. And look, you have a mass 5 kg, and you have a final velocity 10 meters per second, and you have an initial velocity 5 meters per second. Plug the number here, you get the work done. Very simple. So again, the change in kinetic energy is equal to the work done. This is called as the work energy theorem. Okay. So I have a work energy theorem, and let us suppose This is the second part of this problem. Let us suppose this displacement is like again let's say 20 meters. First portion, no displacement, no force. You calculate the work done and you plug the number here like this. 1/2 5 kg and finally is 10 meter per second square. This is your final velocity. 1/2 5 kg and this is your 5 meter per second. You have to square this. So whatever you get, this is your 10 square is 100. Divided by 250, it is I think 250 joule. Okay, and this is how much? This is 5 square 25, 25 times 5, 125. I think this is please do this 62.5 joule. Please check this, okay? Please check this. I don't have a calculator here. So what is this then? 187.5 joule. Please check my calculation, okay? I just do it. I don't have any calculator. It may be wrong. Please check everyone. Okay, so this is the work done. First you do this. Now the second part, the displacement is given. Your displacement D is now 20 meters. How much force you apply there? Calculate the force. Again, this is simple. Again, this is simple. How? You have a work done. Your work done is 187.5 joule. This is the work done. But from our previous topics, work done topics, we define the work done is force times displacement. Okay, so this is 187.5 joule. Okay, from here, look, we are looking for force, but displacement is given F, and your displacement is 20 meters. 20 meters. This is equal to 187.5 joule. Okay, so you have only force there. Divide by 20 meters here. Divide by 20 meters here. Divide by 20 meters there. So whatever you get, your force is 187.5 joule divided by 20 meter. Whatever number you get, please calculate. I don't have a calculator. Whatever number you get, this is Newton. So you calculate the force there. First you use the work energy theorem, calculate the work done. Then use the work done formula F times D, you can calculate the force. Or if the force is given and asking for the displacement, you do the same thing. If the force is given and asking for the displacement, please do the same thing. Plug the force here and solve for the displacement. That is the same thing. Okay. So far we talk about the work done and kinetic energy. Kinetic energy, both work done and kinetic, they are really useful quantity, useful terms in physics. So I want to stop here, but next video I will start from the gravitational potential energy, conservation of energy, and power, elastic potential energy, that kind of thing. So next video I will complete this chapter. Okay guys, thank you for watching. Thank you.